It probably requires very little introduction from me. The two speakers, they are both well known within the research and actuarial community. On my left, I've got Andrew Smith, who is a partner at Deloitte. He's been there for quite a long time. He was telling me just how long he has been at that employer and previous associated employers, and certainly if he continues to exhibit similar longevity, I will be very, very impressed indeed, and that company will have benefited considerably from his skills. We've got, on my right, we've got Andreas Tsanakas, who is a reader in actuarial science at Cass Business School. I don't know if there's anybody here who has come through the Cass Business School, but no doubt you know him well if that is your background. So I'd like to ask Andrew to start the presentation and maybe just to provide a little bit of introduction about the background to the presentation and why we're having this meeting today. Thank you.
Thank you all for coming. It's a great pleasure to give this talk tonight. Just to give you a little bit of background of what this talk is about. This is the subtitle is an update on recent research in the area of quant approaches to model uncertainty. There is not one specific sessional paper that relates to this work. Rather, this is a review of related work. So at the end of the presentation, there are quite detailed references to papers by ourselves, because both Andrew and I have worked in this area mostly independently, but in sort of quite frequent dialogue for a number of years. After the event, we will put up the slides with detailed speaker notes so that you can refer to them and have also a more structured guide to the literature if you want to read further. So let me just start. Now, the presentation has different parts. I will cover the first couple of parts, an introductory section on what we know and what we don't know, and talk about statistical estimation and bias. And then I will hand over to Andrew, who will cover a variety of aspects of the same problem of quantifying and addressing model uncertainty. Now, before we get into the material, start with two quotes. So the first one talks about a blind man in a black room seeking for a black cat, which isn't there. And this is sort of sadly very often our own experience when we are trying to identify the right model. But, and we are like this man looking a blind man in a dark room. But so we have to think that this sort of definition has been used as a definition of metaphysics, and which is not really in our job description, and we don't have the training to pursue. So if we want to do statistical modeling, we can't be really looking for the right model because we're never going to find it. So what we usually do is look for a hypothesis that is consistent with the data, and at least that's a simple hypothesis. And as the great astronomer of old has observed. But of course, this focus on a simple model presents its own complications and limitations, and this is, to an extent, what we're exploring today. Now, moving to the first section, just as an example for motivation, what this plot shows is different estimates of the distributions of yearly equity returns for the FTSE 100. That's based on 30 years experience. So you've got 30 years of annual equity returns, fit a distribution to that. Now, when you do this, of course, you can start at any date in the year and start calculating returns from that date. There's a huge sensitivity to the starting date that you choose. So on the left, you have a distribution if you start in August. On the right, you have a distribution start in October. On the left, And the 1 in 200 years event, the 0.5, well, the 99.5% of your corresponding loss, corresponds to 35% inequities, falling equities. On the right, it's 50% falling equities. So the same statistical scenario. But the only difference between the two is a pretty arbitrary choice of starting date. And there's no judgment separating the two. Right? It's just an arbitrary modeling change. Modeling choice. So that already goes somewhere to demonstrate the level of uncertainty we're exposed to when dealing, especially when dealing with small or even moderate data sets. Now, of course, the regulators have something to say about model error and model uncertainty. So under Solvency II, two things have been said. The one is that the outputs of our model should not include material error or estimation error. And this is a nice thing to require, but we cannot satisfy it. Right? So we can never provide a guarantee that, even in principle, we cannot provide a guarantee that models are error-free. But in general, in the context of statistical uncertainties, we can never say that our estimates are correct. So we can try, but we'll never get there. But the other thing that comes to Solvency II is a requirement that wherever possible, the probability distribution should be adjusted to account for model error. And this is something that we can do something about, right? At least in principle. It might not be easy, but at least it's a problem that we can meaningfully start to address. So, so the way to think about this sort of problem is that, well, in statistics, you can never say that your estimates are right. So you're required to estimate extreme percentiles and extreme events more generally. And you can never say that the estimates are right. What you can say is whether the method that you use in calculating these estimates is good. So this is so what you can say is that you satisfy a particular statistical quality criterion. And this is what will lead you towards finding an appropriate way to adjust probability distributions for model uncertainty. So the question then is, well, how are we going to provide this adjustment? What do we mean by a good method? So this is where we're getting into now by this discussion of biases in statistical estimation. So for this, I will start with a very basic definition of the bias in statistics. So the situation here is that you have observed a sample, which is the yellow area here, and what you want is you want to work on a particular parameter from the sample. So you apply some sort of algorithm to it, pick a square, average, or something like that. Okay. But now, what you have to think is that not only is the future element, but also the past observations that we have are themselves the results of the random process. So yes, you may have this particular sample, and yes, this may lead to this particular parameter estimate. However, you could have had a different sample, right? And each different sample that you could have observed would give you a different parameter estimate. So this is, and this observation is the foundation of statistical inference. But it's rarely discussed in depth because it's fairly counterintuitive, because we think in terms of probability modeling, we think about different futures, right? And assign probabilities to those. But here, in statistical inference, we have to think about different pasts, about different ways that the past could have been. And then, so when we talk about bias, we think, well, what are all the different parameter estimates that we could have worked out under different samples that could have been observed? So not only the one we're seeing, but all the parallel universe we haven't had the chance of experiencing. And if we take the average of a parameter estimate over those alternative histories and find that this is actually, this average is the same as a true but unknown parameter, then we say that we have an unbiased estimator. And this is very well established in this sort of statistical textbook stuff. Now, the problem with bias is that you have to decide which quantity you actually want to be unbiased. Because you can start with collecting some data, these pre-calibrated losses. You can work out moments or mean standard deviations. You can work out parameters. You can work out your required capital. At each of those points, you can require that you have unbiased estimates. But if you, for example, have an unbiased estimate of model parameters, you end up with a biased estimate of capital. If you have an unbiased estimate of capital, you have a biased estimate of standard deviations, because all of these are nonlinear transformations of each other. So we have to focus specifically on what is the quantity we think is important or is interesting here. And as part of this, what we think is interesting, especially for the purposes of solvency type calculations, is a difference between two quantities. One is a random quantity, which is the loss that you will experience in the next period, which is a random quantity, something that appears in the future. And there's a difference of this and your capital. But your capital is itself a function of your data. It has been estimated in some way. And these data, following the previous reasoning, is in itself random. So, and we call this difference a shortfall. So the shortfall is a difference between the loss that we will experience and the capital that we have estimated. And both of these are uncertain in their own way. Right? One corresponds to an uncertain future, and the other one to an uncertain past with the interpretation that I've just given. Now, and this, of course, these sort of considerations relate to the discussion of events not in the data, so of extreme events and rare events which may not be in your observed sample. So there may be some big losses that could have happened, but we happen to not observe them. And within those samples where these losses took place, they would actually give you a very different parameter estimate. But the problem is that if in our observed sample we don't have such events, then we're probably understating capital. If we actually had such extreme events in a sample, we're probably overstating capital. So the only way to think about these constructively is to actually think about the distribution across all different possible samples, considering both scenarios where these extreme events happen and not happen. Now moving along, so let's just introduce a formal framework for discussing these ideas. So what we are interested in, say, is the 99% value at risk for a particular random variable, call it y. So that's our future loss. And what we do is we collect a sample x, right? These are our data. And it's just, keeping things simple, that the data from the same distribution as your future loss. And what you say now is you have something called an estimation procedure. And the estimation procedure is nothing but some function g, which can be extremely simple, like sort your data and take the fifth largest, or something extremely complicated. And what this function does, it takes your data and works out a var estimate from it. Now, so now we have to formulate a requirement for the quality of our value at risk estimate, so essentially of our estimation procedure. So to start this, we think, well, what does var do? Right? So if var 2 is this true value at risk, this true but unknown quantity that should be our capital, this is defined as this value where such that the probability of the loss being smaller than the true value at risk is 99%. So essentially what we're requiring is that only once in 100 time periods should we observe a loss which is bigger than our capital. So in our kind of world now, shortfall unbiasedness, or let's say the quality criterion for estimators, what we say is we keep the same equation, the same condition in place, but now what we're comparing is the future loss with the estimated capital. And we say we want the probability that the future loss being smaller than the estimated capital to be 99%. But now both sides are random here. So this is the big difference. And so in this expression, you actually allow for both the randomness of the future and of the past. And there is a specific precedent in the literature on this. So this kind of we sort of thought we invented independently, but we found out that it exists in statistics under the name of a predictive limit. So there's a noble tradition to these sort of things. Now, if we want to think about what this means, this criterion means, one way of thinking about it is to first consider backtesting. So when you do backtesting of capital requirements, what do? You observe historical VAR estimates and historical losses, and you count the number of times that your historical losses have been above your VAR estimates. And these you call violations. So if these violations are very frequent, then it means that your VAR estimate doesn't work. Now, so what we are doing is something like that. So we call this Monte Carlo backtesting. So what we do is, so if you think about how you would evaluate this probability of future loss being smaller than estimated capital, what you would do is you would simulate a lot of futures for your loss. And you would also simulate a lot of past data histories. And in this way, you would simulate many capital requirements. Right? Estimate capital requirements. And then you would compare the two, and you say, well, how often is the simulated future loss actually bigger than the simulated capital requirement? So this is the comparison you make. Now, if you view this schematically, what you have is the following situation. So you start with a reference model. So you start with a model that you have estimated, and you say, okay, let's now pretend that this model is a true one. So what we simulate is we simulate in two ways. On the one hand, we kind of simulate claims and future and assets. So we simulate the future, which gives us an idea of what the losses would be in the next time period. At the same time, we use a parallel path and also simulate claim and asset histories, which would lead to parameter estimates, which itself would lead to, maybe via simulation, to estimates of our extreme loss percentile. So in the end, we compare the two. We compare the future losses with the capital estimates and count the number of exceptions. So this is, let's say, the procedure. So what sort of results can be seen from that? So the first example here, which is really a pedagogical example, if you like, is as often with pedagogical examples, the normal distribution. So what is plotted here is the expected frequency of exceptions, the expected frequency of violations, right? The expected frequency of future losses being larger than capital, assuming that the underlying model is normal, and the sort of standard MLE estimation procedure is followed. So the two lines correspond to a 99 and 99.5 fifth percentile. On the vertical axis, we've got the frequency of exception, and the horizontal axis, we've got the sample size. So what you see is that if you say, for example, start with a blue curve, so if you only have 20 observations, your actual frequency of exception is 2%, as opposed to 1%, which is what you would like to have. So this is essentially, so if you then compare this 2% with the 1% of your nominal exception rate, the difference between those two is what we call shortfall bias in that context. Right? So it's the additional frequency of violations that you would observe because of parameter uncertainty. And what you see is, of course, as your sample size increases, this curve slopes downwards. So things get better, right? But they don't ever get quite right. So the question is, what can you do about this? And within a simple example like this, actually you can do something pretty straightforward. You can find an algorithm for adjusting your estimates such that your expected frequency of exception is the correct one. It's a nominal one of 1% or 0.5% or whatever. In a way to do this, one of the ways of doing this, is to actually adjust the confidence level of your capital calculation. So what you can say is, well, I start with 99% is the nominal level, but if I only have, so let's say, 40 data points, I will actually have to use 99.4% out of the 99%. And as your sample size increases, let's say the penalty becomes smaller. So this in itself
albeit in a simple example, is a very, very explicit capital add-on that you can produce. So essentially, it addresses the regulatory concern that distributions have to be adjusted, or at least that estimates, capital estimates have to be adjusted. Well, this is an adjustment. It's important to know that this doesn't mean that if you do this, your capital will be right? Because if you got 20 data, you got 20 data. That's all the information you got. This problem is not solved by maths. What it means is that on average, you'll get things right in a certain sense. Now, so the question then is, how often can this procedure be followed? That's how often, when, in which sort of circumstances can you produce these sort of corrections easily? And if the distribution is nicely behaved, something like a log normal or a log t or a Pareto, you can do this easily. If a distribution is not so well behaved, you can still do something which gets you close enough approximation. So you can use an approximate method to achieve the same results, more or less. However, the problem is with all this, so the distribution has to be known. Right? So that's the elephant in the room. It's not really what sort of distribution you have. It's that you don't know which one it is. Right? Because if you don't know it, you cannot do any of the fancy adjustments. So say, well, what next? Well, if we are to consider this problem that we need to know the distribution, we have to consider the process by which the distribution is chosen. Right? And consider this as an intrinsic part of the capital setting process. So here is one recipe for working out what the distribution is. And it's not necessarily what textbooks recommend, but it's something that is often done in practice. So you start with the data, decide what sort of family of distributions you're looking at, let's say normal, estimate the parameters, get the failure distribution, and then perform a goodness of fit test. If your distribution is not rejected, you stop. If it is rejected, you look for another one, and go all the way until you find one that fits in the end. Now, so here is the output from a simulation experiment considering this. So what we have here is, first of all, we're looking at value at risk estimation at 99%. And we have two different reference models, or two different models from which futures and data are simulated. One is a normal, and one is a T with 4 degrees of freedom. And that's the columns, and the rows, we've got 3 different estimation procedures. So one is a normal MLE. So we assume a normal distribution, apply an MLE, and make actually an adjustment to correct for shortfall bias. The second one is a normal MLE where we don't make such an adjustment. So what you see is that if the true model is normal and the MLE, and we apply the normal MLE with adjustment, the frequency of exception is 1%, which is as it should be. If we don't apply the correction, right, it's 1.6. So it got 0.6% extra by exceptions. Now, what if our model was actually wrong? Right? So if the true model was a T, things get even worse because the exception rate from 1.6% goes to 2.2%. Right? So the model error actually increases your frequency of exceptions even further. And now we say, well, what if, can we sort of help this a bit? Can we bring this down if we actually, rather than assuming that our model is a normal, if we actually apply a model fitting procedure, as I described before? And in fact, it doesn't help at all. And the reason is that in this estimation procedure, we start by first fitting a normal model. And then if it's rejected, we consider other models leading up to the T. But with small data sizes, you usually don't reject any model. Statistical tests don't have power. So you're stuck with the first one you tested, which happens to be the wrong one. So we're not really saved by this. We can improve on it, right? but it's not a problem that we can really solve in this way. Now, to conclude my part of this talk, all the discussion so far has been on value at risk. But what about other risk measures? So can this sort of discussion of shortfall bias and of the quality of capital estimates be transferred to other risk measures? And one way of providing a generalization like this is by the following argument, the quality criterion we described was that the probability that the future loss is smaller than the estimated capital is, say, 99%. This is mathematically equivalent to saying that if you take the shortfall, the difference between your future loss and your estimated capital, that you want the value at risk of the shortfall to be 0. So mathematically, that's just equivalent to what we said before. So if you take the difference between future loss and estimated capital, both random, that's your random shortfall, the var of this must be 0. That's what you require. Well, to move to tail value at risk, the only thing that you need to do is change the risk measure. So let's say that our requirement is that the tail value at risk of the shortfall, right, when you're using a tail value at risk estimate, that should be 0. And then you say, well, what sort of adjustments do you need to perform to achieve this? And here what we show is results based again on a normal model. And what the figures show are the number by which you have to multiply the sample standard deviation in order to get, let's say, the right estimator. So if you had an infinite number of data, so you would have exactly the right standard deviation, these would be the multipliers that give you a capital for var and for tail value at risk. But because you have a limited sample, as the sample size decreases, right, the multiple of standard deviation that you have to use becomes bigger and bigger. And so it leads to an increase in capital of up to 40%. And that's both for value at risk and tail value at risk, so the change of risk measure doesn't save you. Okay? And it demonstrates this quite clearly, let's say, the costs of parameter uncertainty in this given context. So I'll hand over to Andrew now.
Thanks, Andreas. I'm going to fill you in a bit of the work that we've done in relation to ambiguity and robustness. One of the problems that we face when we're fitting models is that how to choose what universe of models to fit. You could decide to fit a small class of models with a small number of parameters, and what you know then is that you'll probably have some stability in those parameter estimates, but also there's very little hope that your small class of models that you've picked actually contains one that's really like the data. An alternative would be to say I'm going to fit a much more complicated model with a much larger number of parameters, and then you've got a bit more reason to be optimistic that the true model, if there is one, looks something like one of the models in your class. But then you're caught with another problem, which is you've got a large number of parameters relative to the number of data points, so you add one new data point, the number completely changes, and the whole thing's unstable. And that's something which I guess many of us grapple with on a daily basis. The body of research called robust statistics gives us a way out of this bind, and I'm going to describe it to you now. You need to distinguish two sets of models. There's a small set, which is what I call the fitting set, and that's the set of models that you're going to fit one from. And there's a larger set called the ambiguity set, and the ambiguity set are all the models that you consider might have generated the data possibly. So the extra step is going to be, you're going to have to keep asking the question, what happens if the real model is something from this big ambiguity set, but the model that I'm fitting is from this much smaller set? Now clearly, in those circumstances, you are not going to end up fitting the right model. You cannot fit the right model because the right model is not in the set that you're fitting. But you might still find that the answer you get from fitting the wrong model is good enough. So your model might not be right, but it might be fit for purpose. And the idea of robust statistics is to investigate what this idea of fitness for purpose, to be able to say, even though I've misspecified the model, the procedure I'm applying is robust to that model being misspecified. So let's consider some of what we do at the moment in this context. Quite a lot of what we do, you pick a model, you put this model through a very laborious process of challenge and validation, and you use that model all the way through your business, and that model becomes the truth. So you've immediately neglected the possibility that any of the other, possibly very nearly as plausible models could have generated the data. Now that's a special case of what I'm showing, where the ambiguity set is very small. Or the stats that we've all learned at university, we would be making the ambiguity set the same as the fitting set. So you always assume that the set of models you're fitting contains a true model. What I'm proposing is that for much of the work we do, the setting that makes sense is to have an ambiguity set that's a lot bigger than the fitting set. And then you're going to find yourself having to do a lot of rather laborious tests to demonstrate that your fairly simple fitting procedure works across a large number of a big ambiguity set of models. One of the aspects that comes out there is you have to be able to define exactly what your fitting procedure is in order to be able to apply it to all these large universes of models. And something that often uncovers is what maybe you've heard of Nassim Taleb, the Black Swan guy. He calls it the model graveyard. All the models that you maybe considered but ended up not using. And we tend to be not really discuss the model graveyard. When you fitted the model that you want, all the other models that you didn't want have been forgotten. But in order to apply these robustness techniques, you have to be able to, as Andreas showed in the bias slides, you have to be able to reapply your method on lots of alternative histories that could have happened. So you need to describe exactly how the graveyard has worked so that you can replicate it. Oops, I've lost my... So how can you say that a fitted model is working even when it's wrong? Well, it comes back to this test that Andreas showed a little bit earlier. You're just needing to show that... Oops, how do I make this light work? Is it the red one? Oh, never point a gun towards yourself. So it comes down to Andreas's criterion, but we've got a slight difference here. We've now got a greater than or equal to. So what's happening? What's happening is you cannot expect to hit 99% for every model in the big ambiguity set. What you'll find is if you craft your adjustments to work for one model in the ambiguity set, for another one, it won't work so well. So the best that you can hope for is to be at least 99% confident. So you might say, well, for some models in the ambiguity set, maybe some more favourable models with thin tails, you'll be more than 99% confident. And you're perhaps thinking, well, aren't you forcing us to be ultra-prudent? Wouldn't we rather be 99% on average rather than 99% of the worst case? Well, in general, you can't formulate 99% on average because you haven't got any notion of the relative likelihood of all of these models in the ambiguity set. It's just a class of models. There's no probability relating to them. What you can do, in a very special case, if you're a Bayesian, is think of a set of weights. And this is one area where the Institute of Faculty paid Valeria Bignozzi and Andreas to do some research. And they investigated, if we do this test for counting the number of exceptions, how well does it work using a Bayesian approach? And the answer they came up with, which is comforting, I suppose, is that if the fitting set, if your Bayesian universe contains everything in the fitting set, in the ambiguity set, then it works quite well. But if your Bayesian prior doesn't contain a big enough set of models, then the thing goes horribly wrong. So the Bayesian sort of gives you what you might expect, that if your Bayesian universe contains the right model, you find it. If the Bayesian model doesn't contain the right model, it's actually not very robust at all. So what are we going to do? Well, here's an alternative. We're going to play with the model quite carefully so that it does work over a larger ambiguity set. And we're going to just do that by fiddling. We don't have a theoretical basis for constructing it. We just do it by trial and error. Now, this hasn't been done very often, but here's one example where it has been done. I'll explain what this chart shows. This is about estimating losses for catastrophes. And what the chart shows, the vertical axis is the exception frequency, or 1 minus the exception frequency. How often do you get losses that are bigger than what you said your capital requirement was? And let's suppose, for the sake of argument, we were trying to set capital at 98% confidence. The green line shows what happens if you fit a log normal distribution to your past data and you use that fitted log normal distribution and you calculate the 99.5th percentile of your fitted log normal distribution. What we're seeing is that actually, even if you've used the 99.5th percentile of your fitted distribution, you still get exceptions more often than 1 in 200. But it doesn't get much worse than 1 in 50. So this method here, because these green lines for fitting the log normal, because they're always above, or at least mostly above the 98% line, That's saying that this is a robust framework which gives you at least 98% confidence, regardless of, in this case, the shape of the reference distribution. So the horizontal axis is different reference distributions, different shapes. So in this case, we've shown by doing a large number of model runs with a not particularly impressive ambiguity set. Our ambiguity set contained log normals and generalized Paretos. We've shown that for that ambiguity set and for fitting log normals, actually, even if the model is misspecified, you still have at least a 98% chance of having enough capital. So that's an example of a robustness calculation. It also shows, incidentally, that if you fit your generalized Pareto distributions, the result completely fails to be robust to misspecification, and in fact is not very good even if the model is correctly specified. So that's maybe not what you would expect. Maybe somebody told you, well, there's a extreme value theory justification for using GPDs and log normal is completely arbitrary. Well, actually, by this measure, by this robustness measure, you're better off using the arbitrary distribution than using the one which appears to have a theoretical basis. So that's an example of a real live robustness calculation. There aren't very many of these out in the actuarial literature. I hope there will be some more in the future. It is quite a lot of effort to produce them, but there is an example of one. Got one more theme to cover, which is validation test materiality. So here's a picture of what happens with modelling as you increase the amount of data. On the horizontal axis, I've got the size of the data set, and the vertical axis, I've got the complexity of the model that you fit. And I guess what you all know is if you've got a small amount of data, it's very difficult to fit a complex model because the parameters are unstable. So if you've got a small data set, you almost always end up fitting a simple model, even though, of course, complex models are capable of generating small data sets. You just wouldn't be able to know what the complex model was. But if we look at the other end of the extreme, on the right-hand side, if you've got huge amounts of data, for example, if you've got a data by individual claim amounts for a motor insurance portfolio, you have the reverse problem, which is that no model really fits. There's always some pattern in your data which your model doesn't capture, and however much you make the model more complicated, you never quite captured everything in the data. And there's a sweet spot in the middle, which is where, like Goldilocks level, the amount of data quantity is just right. You can pin down one model and you know what that model is. So I'm going to look now at the right-hand side and think about that in a bit more detail. And the concept that I'm going to bring here is of test materiality. So I'm saying that for large data sets, some tests will fail, but it might not matter if the way in which that test is failing is not material for your purpose. So let's take an example. Suppose I had some distributions of claims from household flooding events, and I looked at those claims and they seem to be roughly a log normal distribution. Somebody else might come along and say, well, I've realised that all of your claims are integer numbers of pence. So they can't be a log normal distribution because a log normal distribution is a continuous distribution. And they could do a statistical test and they could conclusively demonstrate that it had not come from a log normal distribution because every one of those thousands of claims was an integer number of pence. So what would I do? I don't say your test is wrong. I say your test is not relevant for how I'm using that distribution. And we need to have a relevance filter for how we do the test. And we've got one example here. Suppose you were fitting a model to some data, normal to some losses. In this example, what's happened is I've got a fit that looks reasonably good over most of the distribution. I do a statistical test, a Kolmogorov-Smirnov test, and it says the model's fine. But when I look out in the tail, actually it's fitting rather badly, and my fitted distribution fails to pick out some of those large observations. So in that case, our test is leading us not to reject a model, but actually the model we fitted is not very useful because the errors are precisely where we're trying to use the model. You could have the converse happening. You could have a situation where the fit of the model actually is not very good in the middle, but it works fine in the tails. And that's quite a common bodge in stochastic modelling. You might fit a normal distribution, obviously not the right shape in the tails, so you bodge up the standard deviation a bit, fits the tails better, now it doesn't fit in the middle. Does that matter? Well, in a fundamental sense, the model is wrong, but then all models are wrong. And the argument that I'm making is that the model could still be useful. So when you're doing your battery of tests, you should be thinking about, is the test that I'm doing relevant to the purpose for which I'm applying this model, or is the test that I'm doing actually sort of a nice-to-have, slightly irrelevant thing? And this starts to challenge perhaps some of the ideas that we've been experiencing in the insurance industry about use tests the idea that you have a model which you use for lots of different purposes. Because the whole concept of test relevance is that for the purpose you're doing it, the model might be fine, and the model might not be fine for some other purpose. So here's a slide which tries to put this into context, and I guess most of you, like me, learned some stats at university and learned some stats doing actuarial exams. And if you look back to the basis of those stats, there were essentially three great statisticians. There was Ronald Fisher, there was Jerzy Neyman, and there was Egon Pearson, who put together frequentist statistics as we know it, and pretty much the way that we're taught it now hasn't changed a great deal since the 1950s. What I'm saying here is that the way that that was crafted isn't necessarily the right way to do it for actuarial applications. So, for example, Ronald Fisher, his main concern was modelling what happens to crop yields when you hybridise certain different plants, which is not the problem most of us in this room are facing. So I think what we need to do is leap forward a little bit and not be afraid to rebuild the foundations so that our day-to-day jobs sit more easily on the foundations that we've built. So some of the ideas of ambiguity sets, for which incidentally the Nobel Prize in Economics last year was awarded for Hansen for his work in that area. The idea of the quality criteria, as Andreas has shown for VAR estimates, the idea of robustness, and the idea of statistical test materiality. These are things which might be new to many of us in these rooms. These are also areas which are continuing to evolve, but I think they're areas which we will need to construct a more solid foundation so that what we're doing on our day-to-day job, we can give a better basis for the way we've done it. We'll look at the last section now about social model validity. And I think what we all know is that being technically valid is not sufficient for a model to get used. And there might be several criteria. On the right-hand side, you've got textbook criteria of unbiasedness and asymptotic efficiency. On the bottom left, you've got commercial criteria of being stable or not requiring excessive capital requirements. And on the vertical axis, on the top of it, we've got the idea of social acceptability. And you might say, well, what is this doing in a scientific discourse? And what Andreas and I have discussed at some length, we've come to the conclusion that social validity deserves much more of a place at the table. So let me give some examples of social validity. Some of you might be building models of mass lapse events. And maybe you've come to the conclusion that a mass lapse event, the 1 in 200, 99.5th percentile, involves 40% of their population lapsing. And perhaps the reason you come to that conclusion is because that's the number that sits in the Solvency II standard formula, and it's also the number that you know your peers are doing, and you kind of know that if you all submit the same number, it's going to be difficult for whoever's approving your internal model to pick you off against your peers. So really, that number is a social convention, just like it's a social convention whether you have to wear a tie to meetings here, and it's a social convention when you eat your food that you hold your fork in your left hand. I think nobody would send Andrew Smith away to get a mathematical proof that the left hand was the right place to hold your fork. But people do send me away to get a mathematical proof of the 40% mass lapse being a 99.5th percentile. And let me tell you, it's just as futile an endeavour. So what we're arguing is you need to accept the legitimacy of social and commercial constraints on modelling decisions. The Model Risk Working Party actually is due to report here, and I'm pleased that our chair is sitting in the audience next March. And there's quite a lot of work that's been done on social acceptability for that paper. If you have social decisions that are masquerading as science, then that inhibits careful thinking, and the sort of applying your mind to think what could go wrong with a model requires a degree, I think, of intellectual honesty and independence, and that gets compromised the moment you start pretending the numbers that you're actually using because it's what the benchmarking told you, and you start relating it to some irrelevant body of data. So I've got a few conclusions, and then you can tell us what you thought of our thoughts. You can never know that a model is right. The best thing you can know is that what you did was a sensible process. If you're thinking about criteria for good models, then you should focus on what comes out at the end of the process, what you're trying to achieve, which in the case of solvency regulation is controlling the number of companies that fail, or controlling the magnitude by which they fail. Focusing unbiasedness criteria and some internal number in the middle of the process, we don't think is very helpful, even though it's often done. We think robust statistics is very helpful, and that would mean avoiding downward capital bias under a wide range, under an ambiguity set of underlying models. Your models don't need to be perfect, and if you think you've proved your model is perfect, you are deluding yourself. Some models will fail on large data set, but a model can still be useful even if it's wrong. So you need to think about your statistical testing in the context of the materiality and the context of the relevance for the purpose that you're using it. And there will always be social and commercial constraints on model choice. So the purpose of validation should be to understand the impact of those constraints rather than to pretend that they've never been applied. At this point, I'm going to hand back to the chair and would love to hear what you have to say. Thank you.
Maybe if I can make just one or two comments myself or some questions. I did notice that you spent a lot of time trying to justify that the results were likely to be unbiased, and I can see the great attraction of that, particularly you were focusing on that. But I note that in modern regulatory thought, there is this tendency to look at the data, and if it doesn't appear to have enough stresses in it, then you are instructed to get rid of some of that data and find some new data that does have more stresses in it. So you are deliberately biasing the output if currently the data set appears to be missing stresses towards ones that do show more extreme outcomes. How would that adjust the prescription that you have proposed in your comments? And maybe I can leave you the way that we can play this.
We've got a few people who want to speak actually. So
Well, maybe we can leave that. We'll let them ponder that question. But maybe did you say that there was some?
No.
No. Okay. Right. Well, maybe I can ask you to answer that particular question, and that will give the other people here further opportunity to think of suitable questions to pose.
This is what we do that. This requirement of biasness doesn't mean to start with that bar estimates have to be unbiased. So this procedure actually produces a positive bias to bar estimates. In relation to the requirement to use biased data, well, essentially we're saying that we could use biased data as an alternative approach of increasing the bar requirements. It's quite ad hoc. I mean, I think it's very reasonable to say that you should not exclude any data that relate to relevant experience. But the idea of considering past histories, right, this already will include the adjustment, because in some of those past histories, these extreme data will be present. The problem, I think, is really a second order problem, where if your original sample does not have a sufficient amount of extremes in it, then when you go back in simulate histories, you may again simulate histories with not sufficient number of extremes in them. So you can only partially address it. But if we are going down the route of saying we should be biasing samples, right, then we have to be thinking carefully about why exactly we want to do this and in which way. So we have to be transparent about what sort of purpose we're serving, as opposed to saying, well, just put more extremes in so it looks bigger.
I think there's possibly a point here about, I haven't talked about the biases that are introduced deliberately by the model when they're cherry picking perhaps certain data series which they know will give the answer they're looking for. This has been largely a technical talk rather than a behavioural talk, but I think we could all think of examples of where other people have perhaps acted in that way, never ourselves. And it may be that this idea to trawl through possible past data sets and find one that is particularly hairy, is a reasonable antidote to what might otherwise be a tendency to trawl through past data sets and pick one that's particularly benign. So I can see it makes logical sense for that when you have an industry which by and large is trying to dupe models to minimise savings capital requirements. It's entirely sensible that regulators might try to dig a bit deeper and discover these model graveyards. And if you regard it as a model graveyard discovery exercise of asking people to come up with particularly bad data sets, I think that can be quite a valuable exercise and is certainly not conflicting with what we're recommending.
Thank you very much. Yeah.
Matt Coke. Thanks for the talk, which was very interesting and thought-provoking. The examples you gave were all around a single risk. I was wondering if you'd given any thought to when you've got multiple risks and you're looking at the problem of how to aggregate the risks robustly.
It's not in this presentation. There is a little bit of work on this. So one of the questions that you can ask is, suppose that you've got 10 different lines of business which actually all have the same expected degree of profitability. But somebody has taken those lines of business and they've taken the historical experience, which will be different for each of them, and they've done some optimization algorithm, which will invariably involve them biasing their portfolio towards the ones that have done historically well. That's something that you can test in this framework, and it definitely does need testing because you quite clearly see that people's business strategy. An example would be the floods that happened in the United States when everybody was avoiding Florida because their model said it's very risky in Florida, so the hurricane hits a little bit further west and nobody's really prepared. So you certainly can do that model. You have to allow then not only for the model calibration process, but the portfolio optimization process that may have gone on as well. So that means in your different parallel historical universes, you're always biasing your actual strategy towards those which, in the corresponding data set, had a very benign history. But unsurprisingly, it's pretty valuable then to have this concept of parallel universes. To give you another example, somebody might advocate a strategy of picking lottery numbers, picking the same numbers that came last week. And on a backtest, that works absolutely brilliantly. On a Monte Carlo backtest, it's obviously complete rubbish because you have to allow for your optimization algorithm applying only on the data that you've got and not knowing the whole model. So the framework can cope with that from a theoretical point of view, and you can do a few limited experiments. I think what is clear is that modeling the entire decision process of a large financial services business nested inside, somehow embedded inside tens of thousands of possible outer scenarios is not something that's easy from a computational point of view. So this isn't something where you can just download a bit of software off the internet, press a button and have those results. At the moment we're at the stage of getting some insights as to how it would work, but there's certainly some steps further to go to industrialize it to the scale of an insurance or a pension fund with a very large number of different risks.
The name's Bernard Bergman. Thank you for a very interesting presentation. I hadn't planned on making any remarks, but just a few random considerations. We talk about the social pressure to get a particular, the 40% mass lapse. But perhaps the biggest social convention of all is the 99.5th centile, which of course is now enshrined in legislation. And just playing devil's advocate, when this was thought up, when the Solvency II started, maybe 10, 15 years ago, taking into account perhaps modeling that was done at the time and the sort of status of the knowledge at the time, perhaps the 99.5th centile was seen to be okay based on when you've got a stable past and not a random past. And maybe the answer is that, well, if we're going to start adjusting our models to allow for random pasts in all of this and to allow for the bias, well, maybe the 99.5 has to come down to 99. Of course, you get rid of the cross subsidies if everybody does it accurately, but the 99.5th percentile is a convention, and if we start getting perhaps too clever by half, then maybe the 99.5 should be amended. The other sort of perhaps only tangentially related point is in all this correction for bias, we've been talking about capital. We've also been talking about the one-year risk measure, and I know I bang on about this quite a lot, but of course there's the other part of capital, the risk margin, which I think probably most people would acknowledge is just a number, and whether it'll actually do on the tin what it says under situations of stress, being able to transfer your business to another party at arm's length where nobody's pricing based on these 6% costs of capital. Are we not polishing the decks on the Titanic, trying to get the correct for bias when the whole thing isn't looked at as a whole, and other considerations as to whether the whole sort of regime actually will work when taking into account both the risk margin and the capital, the SCR?
Can I just add my own comments? First of all, to say, please feel free to comment or raise issues on what other people have said in the discussion, as well as Andrew and Andreas's presentation. So it would be really great if we could get a good discussion, multi-way going this evening. I just want to say on that risk margin point, I remember making exactly the same kind of comments, but unfortunately the person I was making them to was the guy who claimed to have actually thought up the 6% cost of capital figure. And he obviously had some good reasons to justify why that was actually the right answer. So these things may appear to us not to make a lot of sense, but sometimes there is greater rationale than meets the eye with that type of computation. But do either of you two have any comments that you want to make?
I can, but let's throw it open and see if anybody does.
John Spain. I'm really interested in the reference. Oh, by the way, I agree with the other people. That was an excellent presentation. Statistics in a friendly manner, something we didn't get when I was a trainee. But going on to social and commercial constraints within model choice, surely they're something that comes afterwards when the boards say, yeah, that's fine, you want us to have a fund of £100 billion to meet the risks. We don't think that could be possible, and it's not clear to me that some of that stuff should be in the model choice modelling before recommendations are made as opposed to afterwards.
Okay. Other questions or comments?
Nirav Macharia. Just to comment on the previous comment that was made around the fact that the 99.5 percentile has been enshrined into the way that we're now running the insurance industry. The parallel, I work in a bank, and so I'm a little voice as an insurer in a bank, and they have very much moved away in the banking industry from the 1 in 200 VAR style approach, because there have been issues that have happened, and they've moved much more to a stress and scenario testing based approach, where management really can understand, well, what are the tests, what are the emerging risks that we're seeing, and running those through their models and seeing what that looks like. And I wonder whether in the insurance industry, if something really bad does ever happen, then we might be in a similar position where all of these complicated models that have been developed, the regulators say, oh, well, actually they were too complicated, nobody really understood them, and we should go back to something more simple.
Interesting comment. Of course, current regulatory requirements in the insurance space do require you to do both advanced style computation and stress and scenario testing, but maybe we're here talking about the degree of weight that we apply to those techniques. Other questions and comments?
David Murray. I guess one of the messages that we might take away in the audience tonight is that if we don't have enough data, then we actually need to go further into the tails than we thought we had to. So to get a 99.5% result, we might need to go to 99.7% or something like that. That's one of the messages I took away at least. But I guess that depends on whether we have got enough data or not. So I'm just interested in whether Andreas and Andrew have a view as to whether as an industry we do have enough data to do what we need to do appropriately. So it seems to me like we've got loads and loads of mortality data, so we ought to be able to get very good tail estimates there. We've also got quite a lot of past data around things like equity risk and other market risks. We probably have quite a lot of data as an industry on persistency risk. Perhaps something like credit risk, you could argue that we don't. And I just wonder whether you've got a view as to which are the areas where Andreas's conclusion that we may need to go more into the tail because of lack of data, where are the pinch points there?
I think in the context of any particular organisation, you'd also have to look at the materiality of the risk to that organisation. But in the work that I've done, you're right, for financial market data, there's quite a lot of history, pretty good equity data for many countries going back to the 1970s. Interest rate data for some countries goes back a lot longer. For the UK, I think it goes back more or less to the Commonwealth, Oliver Cromwell era. So the data is there, and the question then comes down to relevance rather than the actual existence of the data points. But there are some areas where the data is very, very much more limited. And I think persistency is one of those. What's now the FCA produces a persistency survey, but you don't have to go back very far before you start getting negative lapse rates and all sorts of other funny things, which it appears nobody now alive can explain. So there's definitely some questions about the data and the relevance and the quality of that data. And if you're looking at particularly mass population behaviours, that's definitely a pinch point. I think another consequence of the way that we've looked at this is that there isn't an abrupt cliff where you've either got enough data or you've not got enough data. There's a smooth graduation where if you've got a small data set, you're going to have to think very hard and make a substantial adjustment for the sampling area in that data. And as you get larger and larger data sets, that adjustment becomes smaller. Now, there may be a stage where you say, the adjustment is so small compared to what I'm trying to measure that it's de minimis and I'm not going to bother doing it. But I think there's quite a lot of the data sets, including some of the ones you mentioned where there's apparently lots of data. I think the model and parameter uncertainty is still a material concern. That's certainly the case for longevity projections, where you might have a huge amount of data, but there's always things in the future which plainly won't replicate that. So, for example, the number of people who've given up smoking in the 20th century cannot be repeated in the 21st century because there are not that many smokers. So it's a slightly facile example, but you get the idea that even when you've got large data sets where there's big social trends that can affect it, the fact that you've got a large data set doesn't necessarily protect you from model uncertainty.
Just to add to this, Andreas said that with large data sets there are structural changes which make them less useful, and the effect of parameter uncertainty also relates on the model complexity of them. When you have large data sets, you also need complex models to describe them successfully. But the other aspect that you raised was that we advise that you should go further in the tail with parameter uncertainty. I would rather phrase it differently. I'd rather say that if you want to specify, to
So what I would welcome is a discussion about what we think is a relevant criterion for managing parameter and model uncertainty, as opposed to what is the right sort of add-on to use.
Matt Modisette. Just to address that issue, I think the criteria you use to go further into the tail is a rather conservative one. You're trying to make a very small chance that your model is understating capital. It's actually not the criteria that I think the regulators use. When they talk about a 1 in 200 estimate of capital, they're not trying to do a conservative estimate of capital. They're trying to do your best estimate of capital, which means it can have an error on either side. So I think that your criteria is a very statistically based one. It's a very natural one if you have a statistical background, but it's probably more conservative than the regulators are thinking of.
Yes, and this picks up on the point made earlier about whether the 99.5% is the right number in the first place.
No, it's slightly different.
Yeah, no, I agree, but it's kind of linked, isn't it?
Andrew Howe, thank you again for a really good paper. Seems to me it takes, understandably, quite a kind of macro approach and clearly focuses on VAR and so on. I wondered if you'd done much thinking about things closer to the mean, if you like, and how a mean might vary according to various parameters. So mortality might be a good example where mortality can vary by lots of factors, some of which are rating factors, others of which are risk factors, which we don't take into account or can't any longer take into account. And just linking it to the point made by someone else about the mass of past data, you know, the mix of those factors may be changing quite rapidly. One example being the pensions market, annuity market, where lots of people may be taking cash out very rapidly. So your techniques work for the mean. Any more thoughts?
So I was going to pick up on when Bernard mentioned particularly the 99.5th and is that the right standard and we're stuck with it coded into regulation. I think a lot of us are focused at the moment on regulatory requirements because they're new and we're trying to keep up with them. Most of the literature that we've drawn on is not about insurance regulation. It's about estimating future outcomes, both extreme and moderate. So the concept of a predictive limit does not have in the description of it a hard coding that alpha is 0.995. You could set alpha equals 0.6 and have a 60% level of confidence if you wanted. And the maths and the concepts still carry across. I think we've hooked a few things on the 99.5 percentile because that's something a lot of us are forced to confront in our day jobs. But I wouldn't want you to think that this set of work was only about complying with regulation. And in fact, I mean, as Bernard and others have pointed out, there are various aspects of the regulation that nobody would necessarily try to justify as being logical because it's the outcome of a process of negotiation and not a process of scientific inquiry. So it would be naive to expect it to come out with something that was theoretically perfect, and indeed it hasn't. But that's kind of not the problem we're trying to fix. We're trying to do a decent job of answering the question posed.
Questions or comments? Or observations on what other people have said?
Hi, my name is David Hare. Like many speakers, I didn't come expecting to say something, but having been in your chair, Malcolm, on numerous occasions, looking around an empty, or at least a full room with no hands waving, I took pity on you. Thank you. I enjoyed this talk as well. I think what it's made me feel is that my knowledge of some statistics is quite inadequate for doing some of the roles that modern actuaries do in life offices. I can use these results, but actually being able to produce them myself is something that would require a certain amount of CPD to get to, if at all I could get to that stage. Of course, the thing that I take comfort in is that it's not a one-pillar solvency regime that we operate in, it's a three-pillar regime. And I go back to the Sharma report from 2002 that highlights that firms get into trouble not because of capital per se, but because of the decisions that management make. So part of what Solvency II, particularly through the ORSA, is doing is highlighting to those making decisions about firms exactly what risks they are running and the consequences of doing that. And I don't think that disagrees with anything that you've said. I think what is highlighted is that the challenge upon us as risk professionals is to take the statistical theory from other areas as well as our knowledge of the financial risks and communicate it to boards in a way that they can actually make decisions that do give policyholders security and shareholders the profits that they're looking for in running firms, whether it, in as wide a range of scenarios going forward as is possible to manage both of those sometimes competing objectives. So I think this is a very helpful paper. I presume it will turn into a paper when it goes into badge that I would encourage many people to read, just to be thinking, as actuaries advising firms and maybe as actuaries taking the decisions in firms, do we know enough about statistics to be really doing a job? And as things move on, is our skill set moving with it to continue to give the quality actuarial advice that we want?
Towards the end of his slide deck, came up with familiar concepts and newer concepts. So can I just have a show of hands? We've got to. Who here has previously come across ambiguity sets of models? This is not very high. So maybe David, you are in good company when it comes to some of this complicated or newer ways of thinking about statistics. Does anybody have any kind of insight into some of the strengths and weaknesses of applying these newer concepts in the sorts of areas we've been talking about? Are we here talking about something really radical that Andrew and Andreas have been kind enough to share with us? Or can we take some of those newer concepts and actually express them in a form that is easier for the layman, if I may put it like that, to actually get to grips with, or the lay actuary at least? Any thoughts on how we make this step to what appears to be a bunch of newer ideas that
Matt Morissette again. I might offer that they're not so new, with no disrespect meant at all, but in an ambiguity set, you have to decide what your universe of distributions you're going to look at. That's not a new concept, but sort of formalizing it into considering what you didn't consider is maybe a little bit of a different angle on it. The entire idea of materiality, every assumption that we make in Solvency II, we have to write down, is it material or not? So it's writing down things that we've been doing for at least a few years. Robustness, these are things that at least I have done and my colleagues have done in our work. Maybe these are a slightly more formalized take on them, but I don't think that these are new animals. They're just in a little bit new clothing, perhaps.
New terminology, perhaps.
Agreed.
I'll put it slightly differently. I think we don't claim to have invented any of these. So in that sense, they're definitely not new. And there are publications going back for decades looking at these questions, although not always applied to actuarial work. So it's a point well made. I think it's also fair to say that a lot of actuaries in their day jobs are doing quite sensible things to their best of their ability. The difficulty is that when you push on the justification for what's been done, the justification doesn't always make a lot of sense. So I'll give you an example. There's a lot of concern about measuring correlations and the possibility that in certain economic scenarios, all those correlations that you've measured historically turn out to be irrelevant, and suddenly everything becomes correlated with each other. And that is a legitimate concern, but it's one that our community has struggled to articulate in statistical terms that would make sense from a pure statistical perspective. So we've got a disconnect between what we're doing. We've got an idea of something that bugs us, and we've got a few bodges that we might do to make us feel a bit better about it. And then you've got these statistical principles where we're trying to articulate it in terms of some principles that doesn't really connect in the middle. And so you end up with a slight wild goose chase that is tail correlation. It's a term you will not find in any statistical textbook. It's a term you will find in pronouncements from regulators, and is a term you will find in consulting marketing literature in which they claim to be able to address on your behalf the concerns of the regulators, but it's actually a completely empty, vacuous concept. It doesn't really exist, and we're struggling to find the language to articulate it. You can articulate that in the context of ambiguity sets. So there's a class of different dependence structures. We know that we don't have enough data to pinpoint which one applies, but what we can do is consider each of those as reference models in an ambiguity set and look at the consequences and understand where our vulnerabilities are. So that would be an example of where you might get current practice a bit more consistent, a bit better codified by rooting it in statistical principles, whereas at the moment it's sort of floating in the ether and not sufficiently grounded to be able to apply really rigorous statistics to it.
Anybody else got any takes on this new concepts?
Patrick Kelleher. Just an observation, as I said, the concept, this is obviously a very simple tool, but the idea of simulating past histories as well, I think that could prove very useful in things like standard formula appropriateness and checking, and demonstrating basically, because you have in some ways a reference distribution, and that particular kind of approach of trying to simulate past could be quite useful in that regard.
This is in itself nothing new, right? So when you can do your first introductory course in statistics and you work out and test the difference of means or something like that, and it's exactly the fundamental ideas on which all statistical testing is based. So it's not really, in some ways, not really so much to do about having concepts which are deeply new. It's more to do with the need to intellectually engage with what is there and try to carefully articulate and formalize kind of our instincts, our insights.
Bernard Bergman again. Just following up on the standard formula comment, have the authors applied any of their techniques, methodologies to actually validate the standard formula model to see whether it actually sort of produces the 99.5th percentile when measured against the data upon which it was calibrated? Does the question ever make sense? But
it does. We have done that, and it fails. If you take randomly generated past histories and you look at the methodology, for example, by which the interest rate stress is calibrated, and you generate lots of alternative pasts, some of those alternative pasts will be very smooth, some of those alternative pasts will be very volatile. Your future outcomes are also generated from the same model, but not necessarily the one you fitted, the one that generated those pasts. And there's a significant number of cases where you underestimate the stress because you've had a luckily smooth past, and at that point, far more than your 1 in 200 trickle through in the future. There are other cases where you overestimate your stress, but the consequence in terms of exceptions, violations is much smaller. So as a rough order of magnitude, the 98%, you'd be doing quite well if you got exceptions of 1 in 50. So the methodology that's been applied to the standard formula was either deliberately or by accident, did not really consider the parameter uncertainty in it. And if you measure it by a metric as we're advocating that does capture the parameter uncertainty, I mean, not just us that are advocating that, that is also required in the level 2 implementing measures, then it manifestly fails.
Yes, well, we are all thinking how are we going to validate that our approaches are consistent with the standard formula if we are using the standard formula, that is. And that kind of ties in also with the comments about maybe the regulators didn't want to be quite as conservative as some of the approaches that might be set, or do you feel that they are not actually quite conservative to do the sort of methodologies that you have highlighted here?
What personally bothers me is the apparent deceit of proclaiming models that are much higher confidence than we all know they really are. So I don't have a strong view as to whether insurers should be required to hold twice as much capital as they currently are, half as much capital, about as much capital in between. That's a political call that's part of the social contract, if you like, between the insurance industry and policyholders. What I find uncomfortable is being expected to say that something is a 1 in 200 event, and actually you've ignored a whole load of things which even the regulations say you're not allowed to ignore. Now, I agree that it's a total muddle, and you do have a standard formula and an option to use that, in which case you don't have to apparently to make those assertions. And so there is a bit of a muddle there. That's personally what bothers me, and it actually ought to worry everybody in this room because it's a threat to the reputation of people who are working in those modelling areas.
We've got, yeah.
Ben Johnson. I'm no statistical expert, so apologies if this is a very basic question. But I've just been thinking that right at the beginning of your very good talk, you raised the idea of model simplicity as being a very important factor and something that we'd look for. And then in the talk, you talked quite a lot about robustness and determining whether a model is sufficiently robust. Where there are more than one model that might satisfy your robustness requirements, how would you then handle the trade-off between robustness and simplicity? I guess in some cases your most simple model might happen to be your most robust model, but where there's a trade-off, what kind of optimization kind of techniques would you use? Is it just a judgment call, or do you have kind of techniques in mind?
So there was a section of the slides which we cut in the interest of time, which looked at that because what we've described is some tests that could be applied, and as you've noticed, you may be able to construct more than one method which passes those tests. So my take on it is that from the point of view of complying with what you've been asked to do, any of those alternative methods should tick the box, and from the point of view of regulatory approval or somebody validating that you're fitting a 1 in 200, it should be a matter of indifference which of those you pick. But the different methods could have several different properties. Some of them might produce capital results which fluctuated more than others over time. Some might produce capital results that explode to very large numbers in certain stress situations, and there'd be a cyclicality problem with those. Some might produce capital requirements that are higher than others on average, and you might want to look at the average capital requirements over the cycle. And that will depend on a firm's individual preferences. You're not going to get a one-size-fits-all. But I think those trade-offs, rather than model simplicity, the trade-offs are if you're going to hit this 99% or 99.5% target, what you can then play around with is measures of volatility of the requirement and measures of the average level of the requirement, and that's roughly where the trade-offs are.
We've probably got time for maybe just one more
So can I thank all the people who have contributed to the discussion. Just before I close, could you, if you have got any prepared transcripts, I didn't see anybody who looked as though they did, but if you do have some and you've made a comment, then please, could you hand those prepared comments to the events team as you leave. So just falls on to me to say thank you very much indeed to Andrew Tsanakas and to Andreas, good try on my part, and Andrew Smith for what I thought was a really great presentation. Thank you for coming along, and thank you for sharing your insights. And could we just thank Andreas and Andrew in the